When one bad batch sends your loss off a cliff, gradient clipping in PyTorch caps the update before training blows up. This is the workflow you'll know how to run when we're done, which configures a gradient clipping threshold and applies it to stabilize updates. I'm Professor Pi, teaching AI foundations with simple Python. Gradient clipping is a safety valve during training. Occasionally, a batch produces enormous gradients. Those spikes can shove weights into nonsense and stop learning cold. If you train deep models or work with noisy data, you'll see this. The goal is steady, meaningful updates and a loss curve that doesn't explode after one unlucky batch. The fix is straightforward. Measure the gradient size, and if it's above a safe threshold, scale it down so the parameter update stays bounded. It won't solve bad data or broken objectives, but it prevents catastrophic steps that would otherwise ruin hours of training. We'll build a compact PyTorch demo, create a spiky batch, measure gradient norms, apply clipping, and run a tiny loop to show clipping keeps updates under control. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To see the problem directly, we start by constructing a linear layer and a deliberately huge input to watch gradients explode. This snippet inspects a PyTorch linear layer to show how a single batch can spike gradient norms. The torch import gives access to tensors, and we build a bias-free linear layer so every input column directly affects the output. By setting each weight to 1 and feeding 3 samples filled with 20, the forward pass produces a very large mean squared loss. Backprop fills model.weight.grad with matching large values, and taking the norm reduces that tensor to a single scalar magnitude. The printed loss and grad norm make it obvious that the gradient magnitude tracks the runaway loss, which signals that training can quickly become unstable. Seeing the raw jump, we next let an optimizer take a step without any guard to show how far parameters can move. To illustrate the damage a single step can inflict, take a clone of the weights before and after the update. Then, compute the Euclidean distance to quantify the jump. This example walks through the same PyTorch module, but lets SGD push parameters without any safeguards. The optimizer is bound to the model parameters with a 0.1 learning rate, so the step is intentionally aggressive. After zeroing any leftover gradients, a fresh loss on the high-valued batch triggers backward and fills the weight gradient buffer again. Cloning the model.weight before the optimizer step lets us measure the Euclidean distance between the old and new weights. The printed loss, step, and update jump show that a single pass can hurl the weights an enormous distance, enough to wreck training dynamics in a deeper network. Now compare a calm batch and a spiky batch to locate which input causes the worst gradient norm. That helps us target clipping behavior. We create 2 batches and compute their gradient norms to rank them and find the worst offender. This identifies which pattern to clip. This code contrasts calmer and spikier PyTorch batches by ranking their gradient norms. Resetting model weights to 1s gives a neutral starting point, while we build a batches dictionary containing a mellow 0.5 tensor and the original spiky data. The loop zeros gradients, recomputes the loss for each batch, and calls backward, so model parameters carry fresh gradient tensors. Collecting those grads into a list and passing them to torch.nn.utils.getTotalNorm computes the combined norm and returns a scalar. Storing that value under each key and then picking the max pinpoints the spike batch, and the printed worst case and grad norm highlight which input would blow up training first. With the worst batch identified, we apply gradient clipping before the optimizer step to see how much it tames the update. We will clip to a chosen max norm, then step the optimizer and compare the parameter motion to the unclipped case. This snippet caps the unstable batch by applying torch.nn.utils.clipGrad norm before any weight update. The code restores the weights, zeros stored gradients, and measures the raw magnitude, so we know how severe the spike is. Cloning the parameters preserves the pre-step values, while the clipping call rescales gradients down to a 50 norm and records the trimmed magnitude. Stepping the optimizer then moves the weights using the softened gradients, and the post-step norm quantifies how much smaller the shift becomes. Lowering max norm squeezes updates harder, and raising it lets more of the spike through. So the printed metrics demonstrate that clipping tames both gradient size and parameter motion. Finally, we wrap this into a tiny training loop that alternates calm and spiky batches and clips every step to simulate realistic repeated surges. This loop tracks running loss and the worst gradient norm seen to show clipping keeps things bounded over time. This example assembles a tiny PyTorch training loop that alternates calm and spiky batches while clipping every step. Resetting weights and using an optimizer with a 0.005 learning rate keeps the baseline consistent with the earlier snippets. Reusing the original spike tensor and scaled variants builds batches that mimic periodic surges you might encounter in practice. Each iteration zeros gradients, computes the loss, clips them to a 25 norm, and updates running trackers for the latest loss and the worst observed norm. The printed final loss and max grad confirm that, even with repeated spikes, clipping enforces a bounded gradient history and keeps the loss from spiraling out. You can drop this pattern straight into a real training loop. Swap the toy layer for your network, feed real batches, and clip to stop single bad batches from derailing long runs. Recap: gradient clipping rescales gradients so their combined norm stays below a threshold. Use it when you see sudden gradient spikes or an exploding loss. This is most common in deep models or noisy data. One caveat: clipping prevents catastrophic steps, but it doesn't fix biased data or a fundamentally broken objective. Next step: tune the clipping threshold and learning rate together to find the smallest threshold that preserves learning without choking progress. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.